In an organic light-emitting diode, or OLED, light is created by injecting electrical current into a specialized carbon-based film. That current consists of negatively charged electrons from one electrode and positively charged holes from the other, colliding within the molecular lattice. This diagram illustrates the macroscopic layer stack of an OLED. When an electron and a hole meet in the central emissive layer, they bind together to form an exciton. This bound electron-hole pair is the primary mechanism for light emission in organic devices. Once formed, this exciton holds a precise amount of energy. The overall efficiency of the display depends entirely on how that exciton sheds its energy, whether it decays by releasing a photon of light or by dissipating into the surrounding material. To understand why a display is bright or dim, we have to track the exact energetic fate of every single electrically generated exciton down to the molecular level. Early fluorescent OLEDs hit a hard physical wall. No matter how perfectly the device was manufactured, engineers found that the internal quantum efficiency was capped at exactly 25%. This flowchart visualizes the problem. 1 million generated excitons split into two streams. A 25% stream yields photons. The massive 75% red branch represents triplet states. These cannot release light. Instead, they decay non-radiatively, dumping their energy as pure waste heat. Quantum mechanics dictates this loss as a statistical baseline, regardless of material purity or manufacturing quality. For every 4 excitons electrically injected, 3 are completely dark. To change this, we have to look inside the exciton itself, down to the level of quantum spin. This diagram breaks down the intrinsic angular momentum, or spin, of our particles. Both the electron and the hole behave as spin 1/2 objects. The spin projection along an axis can either point up, represented as plus 1/2, or down as minus 1/2. When an electron and a hole recombine to form an exciton, their individual spins add together. Because there are only 2 particles with 2 possible directions each, there is a strictly limited number of ways their spins can align. This 2x2 matrix maps those combinations out. You have the electron spin up or down on one axis and the hole spin up or down on the other, giving us exactly 4 raw state combinations for the newly formed exciton. These raw combinations organize into distinct total spin states. Looking at the left panel, one of these is the singlet state. Here, the electron and hole spins are antiparallel and cancel each other out entirely, leaving a total spin of 0. There is only one way to form this state. The other 3 combinations form the triplet states. In these configurations, the spins do not cancel, giving the electron-hole pair a total spin of 1. As the multiplicity equation shows, there are 3 distinct triplet variations. Because all 4 configurations are equally likely during electrical injection, we arrive at a strict mathematical ratio. Recombination naturally creates 1 singlet exciton for every 3 triplet excitons. Creating an excitron is only the first stage.
For that exciton to emit light, it must drop from its excited state back down to the ground state. That drop is governed by strict transition rules. This energy level diagram illustrates the primary barrier, the spin selection rule. Simply put, an optical transition is allowed only if the total spin does not change during the drop. Delta S must equal 0. Because the natural ground state of most organic molecules is a singlet with a total spin of 0, an excited singlet exciton can drop straight down. 0 minus 0 is 0, so it smoothly releases its energy as a photon. A triplet exciton has a total spin of 1. To reach the singlet ground state, it would have to change its spin. Under simple quantum rules, this transition is formally forbidden. This exact mechanism causes the 75% waste bottleneck. Because the 3 triplets cannot radiatively decay into the singlet ground state, they are trapped. The energy has nowhere to go but out into the material as heat. To push displays past that 25% limit, engineers had to find a way to bypass the selection rules and access the majority triplet population. This diagram shows the primary physical hurdle, the energy splitting gap between the higher singlet state and the lower triplet state, denoted as delta E(ST). The first major breakthrough was phosphorescent OLED technology. By doping the emissive layer with heavy metal atoms like iridium, chemists altered the local quantum environment. Here we see how that works. The heavy metal atom creates strong spin-orbit coupling. This effect mixes the characteristics of singlets and triplets together, relaxing the strict spin conservation rule and allowing the triplet to emit a photon directly. By fundamentally weakening the strict spin conservation rule, phosphorescence converts the 75% thermodynamic loss into usable light. Heavy metals are incredibly effective, but they are also expensive and rare. A newer technique, thermally activated delayed fluorescence, or TADF, harvests those same triplets using entirely different physics. Instead of forcing the triplet to emit directly, TADF requires precise molecular engineering. The goal is to minimize exchange interactions within the molecule so that the energy gap between the singlet and triplet states shrinks to almost zero. This cyclic diagram illustrates the thermal bypass. Because the energy gap is engineered to be incredibly small, standard ambient heat in the device provides enough energy to bump a triplet exciton back up into a singlet state. This process, known as reverse intersystem crossing, acts as a continuous recycling mechanism. It converts dark triplets back into bright singlets, which can then radiatively decay without violating the spin selection rules. Looking back at our flowchart, the 750,000 dark triplets are no longer dumped as heat. Instead, they route through the TADF converter, merging back into the blue light-emitting stream. The mathematical payoff is immense. Factoring in radiative efficiencies, internal photon production surges from 200,000 to 680,000. Modern display engineering is a continuous battle against these hard physical limits. Controlling subatomic spin statistics directly determines the upper limit of macroscopic display efficiency.